Okay, good evening and welcome to the Vancouver Kimberlite cluster. Thanks for tuning in virtually from, I think, all over the world. I would like to introduce myself. I'm Catherine Landoni, a master's student at University of British Columbia, and I am studying under Kelly Russell, and I will be the VKC host for this year. I have here with me virtually Barbara Scott-Smith, who was chatting away beforehand. She's an adjunct professor at UBC, and she's going to be the convener for 2021 VKC series while Maya is on sabbatical and taking a well-deserved rest. So VKC is a series of seminars for diamond geology and related topics. And the main goal is to bring academics and industry professionals together so that we can start chatting. I want to acknowledge SRK Consulting for being a longstanding VKC sponsor. And thank you. I know that we are pretty well versed with Zoom at this point, but I just want to share a few housekeeping notes. So the first is that I want you to keep your microphones and cameras off during the presentation because it will help increase the quality of the streaming. The presentation will be about 50 minutes long, so please keep your questions till the end, and then we'll have a questions and answer period that I will facilitate. So I'm delighted to welcome a fellow Diamond Exploration Research Training School student, Nicole Meyer. Nicole just successfully defended her PhD about a month ago at the University of Alberta, so congratulations, that's amazing. Nicole started her studies at the University of Cape Town and received her geology undergraduate degree, and then she also got her master's at the University of Cape Town in chemical engineering. In 2015, she moved to Canada to pursue her PhD at the University of Alberta. And throughout her time at the University of Alberta, she researched Koffiefontein diamonds and was supervised by Thomas Satchell and Graham Pearson. She's currently wrapping up some of her PhD work loose ends over there and is looking for postdoctoral positions at the moment. In her free time, she's an avid runner and photographer, but now we'll let her tell us a little bit more about Koffiefontein diamonds. Okay, I'll stop sharing my screen and hand it over to you.
Thanks, Catherine. Okay, so let's get this shared. Okay, everybody should hopefully be able to see this. Great, so I'm just going to head straight in. So thank you everybody for coming to my talk, for tuning in. And I'm going to be talking about diamonds and their inclusions from the Koffiefontein mine. So hopefully you'll enjoy this. If not, there are plenty of pictures to keep you entertained throughout. So for my talk today, I'd like to take you on a journey through the mantle, from the lithosphere to the lower mantle, and what diamonds and their mineral inclusions can tell us about the environment and mechanism of diamond formation. Diamonds form under great pressure and temperature within the subcontinental lithospheric mantle, the rigid region of the mantle beneath cratons. Of the diamonds that form, only 1% encapsulate minerals. Diamonds preserve these minerals due to its robust nature, and because diamonds vary in age, they preserve a range of environments all the way back into the Archean. Below is a cross-section of the Craton showing the deep roots of the SLM where diamonds form. So the minerals included within diamonds capture the chemical environment related to Craton formation and modification. Diamonds made mainly of carbon and trace amounts of nitrogen also record the movement of low concentration volatiles within the mantle, and importantly, the deep carbon cycle. Although the vast majority of diamonds form within the Cratonic lithospheric mantle, some diamonds originate from the asthenosphere and even as deep as the lower mantle. These diamonds provide information about the deepest parts of the accessible Earth. Below are two examples of inclusions within diamond. On the left are purple Peridotitic garnets, and on the right, an eclogitic sulfide. Both diamonds are from this study. Here is a map of the Kaapvaal Craton in Southern Africa. The Kaapvaal Craton formed from two proto-cratons, the Kimberley block in the west and the Witwatersrand block in the east, and is surrounded by the Proterozoic terrains at its margins. Together, the Kaapvaal and Zimbabwe cratons make up the Kalahari Shield. The Koffiefontein pipe is located on the Kimberley block, close to the suture with the Witwatersrand block. It is a group 1 kimberlite that erupted in the Cretaceous. The Koffiefontein pipe has been in production intermittently since the 1870s, generating millions of diamonds. The diamonds are characterized by a mainly peridotic silicate population, a significant population of sulfide-included eclogitic diamonds that are 2.9 billion years old and date the merger of the two cratons, and a younger population at 1.2 billion years old. A significant cloudy diamond population that formed shortly before Kimberlite eruption, and an exclusively Peridotitic lower mantle suite. At the bottom is a photograph of Koffiefontein when it was still an open pit, early in the mine's history. From the Koffiefontein diamonds and diamonds worldwide, there are still questions left to be answered. For diamonds, it is the source of the diamond-forming fluids and their reactions that precipitate its formation. For the included minerals, it is specific to how the cratons formed and its chemical and tectonothermal evolution. And for sublithospheric diamonds, it is the source of the diamond-forming fluids and their included minerals. To answer these questions, I set about a study of almost 200 diamonds over almost 5 years. The following presentation is split into these 3 sections. And although I performed many analyses, I have selected only a few to discuss. So heading straight in, I'm going to start with the physical characteristics of the diamonds. From the 189 diamonds studied, more than half were peridotitic, a few were websteritic, and the remainder were eclogitic, either with silicate or sulfide inclusions. In terms of the diamond's physical features, I have summarized them here. The diamonds are generally colorless, with a few yellow and brown diamonds. The yellow diamonds are very light yellow, whereas the brown diamonds can be light brown or a very intense brown. With regards to shape, octahedra and twin diamonds are common in the peridotitic suite, whereas dodecahedroids and irregular shaped diamonds are more common in the eclogitic suite. It may be hard to imagine just by looking at these 2 pie charts what these features and colors really look like, especially if you've not worked with diamonds before. So I've selected a few images from my Koffiefontein diamonds to display some specific features. So firstly, in color, this diamond displays a rich, deep brown color, and commonly with brown diamonds, you get striations, but I'm going to show you that in a few slides' time. I showed these 2 images earlier, but I'm repeating them because they're great examples of shape. Primary octahedra were common in the peridotitic diamonds, and dodecahedroids were most common in eclogitic diamonds. And rarely, there were examples of a diamond in transition between an octahedra and a dodecahedroid. If you're unfamiliar with the resorption of diamonds, I've included a diagram on the left that shows how it changes from an octahedral to a dodecahedral shape during resorption. And here I've outlined the remnant octahedral face with the trigons preserved. Twin diamonds were also common. The most common twin type is the spinel twin, also known as a macle. Here is a twin with an included olivine, and you can note the graphite that surrounds both the olivine and on its surface. And here is another macle twin plane, with a twin plane visible over here. And another interesting resorption feature is the circular erosion sculpture. I've highlighted the circular shaped flat bottom pits here. It is opposite to a microdisc in that its relief is negative. So I may have just bombarded you with a lot of diamond images. These were mainly related to color and shape and some surface feature. Another aspect of these diamonds is its deformation. Diamonds sit in the mantle for long periods of time at high pressure and temperature. At these conditions, diamonds can accommodate a strain in a form of plastic deformation, which is generally expressed as parallel striations. And here is an example in a brown diamond. The striations are highlighted here. But also on a colorless to lightly colored diamonds. And less commonly as coarse plastic deformation, as seen by these lines that appear to look like fractures. And yes, that is a twin plane too. And here's another example. So I've spoken a lot about the color and shape of these diamonds and some unique features. I hope this has given you some insight as to what the Koffiefontein inclusion-bearing diamonds look like. So now straight into some analytical results. So before we get into any specific results, the most abundant impurity in diamond is nitrogen. It substitutes for carbon in the diamond lattice in a few different ways. With time and energy in the form of heat, the substituted nitrogens move from single bonded to doubly bonded. And with even more time and heat, it forms 4 nitrogens atoms surrounding a vacancy. But why is this important? We can use this information to calculate the temperature of the mantle where these diamonds reside. Using Fourier transform infrared spectroscopy, FTIR, I analyzed for nitrogen concentration and aggregation. Koffiefontein has a high proportion of diamonds with no detectable nitrogen, so that's seen all the way to the left of the diagram. The diamonds that have a high concentrations of nitrogen are more commonly the eclogitic diamonds, and this is not unusual and seen at many locations. So the eclogitic diamonds are in the yellow and orange colors. Using the nitrogen concentration and aggregation and an estimated time of 2 billion years in the mantle, I calculated the temperature experienced by these diamonds during their time in the mantle. The Koffiefontein diamonds have a tight temperature range between 1050 and 1225 degrees Celsius. This is similar to other diamonds from the wider Kalahari Craton, as shown by the large hump in the red kernel density line. The higher temperatures derived from the fully aggregated diamonds are restricted to the peridotitic suite, and one diamond even has a temperature as high as 1410 degrees. For those unfamiliar with isotopes, you can measure the carbon and nitrogen isotopic ratio in diamond. For carbon, it's 13/12, and for nitrogen, it's 15/14. As nitrogen is a trace element, for SIMS, about 100 ppm of nitrogen needs to be present for a reliable terminology. And just some terminology, if it's depleted in 13C or 15N, the values are more negative, and the opposite is true for 13C and 15N enrichment. Okay, now on to some results. From the 189 diamonds studied, a representative number of diamond fragments were analyzed for carbon and nitrogen isotopes by SIMS. The cathodoluminescence image on the right shows a transect through selected diamonds. The brighter regions, which indicate higher nitrogen contents, outline numerous growth events. These can have vastly different isotopic signatures, but in general, the within diamond delta 13C values do not vary by more than about 1 per mole. The same is not true for delta 15N. This highlights the problem in getting a representative analysis when diamonds contain multiple and complex growth histories. Thus, both spot and bulk analyses cannot always be representative. For example, diamond 10-07 has a fully resorbed core and multiple subsequent growth events, whereas diamond 10-04 has a twin plane highlighted in red with multiple possibly continuous growth events. The delta 13C of the mantle is -5 per mole. This is mirrored by the delta 13C of peridotic diamonds, but eclogitic diamonds have a much larger range with a noticeable 13C depletion. This is a result of subduction, which can incorporate biogenic carbon and carbonate rocks. Additionally, different species of carbon in mantle fluids or melts, for example, carbonate or methane, can vary the delta 13C values of diamond, but this is less pronounced for carbon than it is for nitrogen. Like diamonds worldwide, the Koffiefontein peridotic diamonds have a dominant mode about -5 per mole and a smaller second mode around -12 per mole. The delta 15N of the mantle is -5 per mole, and diamonds range between +15 to -25 per mole. Nitrogen in mantle fluids or melts is low, and thus the nitrogen is susceptible to fractionation due to reservoir effects. Nitrogen enters the mantle in subducted sediment. Like carbon, nitrogen in diamond-forming fluids can take on multiple species, which they can readily fractionate during diamond formation. The Koffiefontein eclogitic diamonds have a strong mode at 0 per mole, whereas the peridotic diamonds have a bimodal distribution about +7 and -5 per mole, and a small population at much more 15N depleted values. Looking at these nitrogen trends in more detail, we can see a crude negative correlation of decreasing nitrogen content and increasing delta 15N for the peridotic diamonds. This is a result of subduction and prograde metamorphism, which increases the delta 15N value. The origin of 15N depleted population is unclear, and current explanations cannot account for values below -12 per mole. Thus, one possible explanation is the nitrogen species in the diamond-forming fluids. However, much more research is needed in this area. Combining the delta 13C on the y-axis and the delta 15N on the x-axis provides a way to fingerprint the origin of diamond-forming fluids. For reference are some possible reservoirs in carbon and nitrogen space and the mantle region in the gray box. Studies have shown that the altered oceanic crust and subducted slabs provide multiple reservoirs, of which I've selected 3 of these to display. These reservoirs are normal carbonate with clay, biogenic carbonate with clay, and a high temperature clay. By mixing different proportions of these reservoirs with mantle-derived carbon and nitrogen, an envelope of possible compositions arise. Adding the Koffiefontein data shows that the majority of the diamonds, both peridotitic and eclogitic, have mantle-like delta 13C signature, which could indicate carbon derived from a subducted slab, and a nitrogen component derived from the devolatilization of sediment on a subducted slab. So what is the source of these diamond-forming fluids? The similarity of the dominant delta 13C mode suggests that the source for peridotic and eclogitic diamonds was the same, likely a subduction scenario, which can generate this range in carbon-rich fluids. Explanations for the origin of 15N depleted diamonds are unconvincing. Although fractionation due to reservoir effects can be large, they are not in the direction of 15N depletion, thus other nitrogen species need to be investigated. Moving on to the mineral inclusions within diamond. From here, we can use the inclusions to tell us about the formation of the Kaapvaal craton and its evolution over the past 3 billion years. Shown on the right are 2 diamonds with silicate inclusions. At the top is a purple peridotic garment, the most common inclusion released from the Koffiefontein diamonds, and at the bottom, a colorless olivine inclusion, which was the second most common inclusion released. From the 91 diamonds that I broke, 209 inclusions were released and analyzed. The vast majority were peridotic. For the mineral inclusions in these diamonds, what insights can we glean as to the formation and modification of the STLM beneath Koffiefontein? Earlier, I showed you pictures of diamond colors and shapes, and next I've selected some images of mineral inclusions within diamonds. How many inclusions can a diamond hold? 2 diamonds each released 9 distinct inclusions. Both had peridotic garnet-orthopyroxene. And 1 lower mantle diamond released 13 discrete inclusions. Is that a purple garnet or a colorless inclusion? Internal reflections are fun in diamonds. This is actually a garnet, and I've outlined what it should where it's sitting over here. And here's another octahedral diamond, but this time it is chock-a-block with many chromite inclusions. They're quite small, but there's still many. And a lozolitic garnet and an olivine. The lozolitic pyrogenesis is uncommon in these diamonds. And an orange pyroxenitic garnet in an irregular shaped diamond. And moving from the silicates to the sulfides, here is a close-up of the rosette around a bunch of sulfides. And an even better one, a close-up of an eclogitic sulfide with a graphite rosette. And if you're unsure what the sulfide looks like, there it is. And the last one, is a diamond within a diamond an inclusion? How do you know it's a diamond? Here you can see the stacked growth plates on the surface of the included diamond over there. So moving from the pictures onto some science, at Koffiefontein, there are a host of mineral inclusions, and these are just a selection of them. So why do we study the mineral inclusions and what can they tell us? Cratons form by basaltic melt removal from upper mantle prototype, forming a buoyant lithosphere that is hard to subduct. Addition of water via subduction leads to crustal differentiation and formation of cratonic nuclei. These nuclei merge to form larger cratons, which are stabilized by metasomatism to produce the cratons we see today. For melt extraction, 2 end-member processes can occur. Melt is either generated shallowly at spreading ridges or deeply by mantle plumes. For the Kaapvaal craton, a shallow melting event is most often implied, but this is a subject of debate. The Koffiefontein peridotic garnets, shown in purple, plot almost exclusively in the Hausbergitic field of the chrome-calcium plots. And for Koffiefontein, there is a significant proportion of low calcium peridotic garnets, shown here in the blue shaded region, that suggests derivation from a denitic host rock. Lozolitic garnets were rare and one Websteritic garnet was recovered. In addition to the low calcium nature of these garnets, they have a high chromium content, up to 13 weight %. This reflects the high bulk rock chrome-aluminium ratio, which arises during shallow melting in the spinel facies, which retains chromium in the residue during partial melting. This chrome-rich residue goes on to form peridotic garnet. And it is also shown by the rare earth element plots, which will be discussed a little later. The Koffiefontein-Olivine inclusions have a very high magnesium number, with values that extend up to 95. This is much higher than olivines from diamonds worldwide, but within the range of other Kaapvaal Craton diamonds. The high magnesium number is generally indicative of extreme levels of depletion, as shown with these experimental melting curves in dashed lines, and their axis is on the right. To achieve such high magnesium number, highly improbable fractions of melt need to be removed, almost 70% at pressures of 7 GPa. How can this happen? Here's a diagram of coexisting olivine and orthopyroxene from both diamonds in the circles and xenoliths in the crosses from Koffiefontein. The mineral inclusions from diamonds plot beyond the chemical boundary of the orthopyroxene out reaction. But OPX is present, and further, it is required for garnet formation. The high modal orthopyroxene in Kaapvaal Cratonic xenoliths in relation to its olivine magnesium number is a well-known phenomenon. Numerous hypotheses have been put forward that rely on melt and/or fluids that have been released from subducted slabs to increase the silica content. But most of these scenarios do not match up with what we know about the Kaapvaal Craton today. Some studies have looked to melt rock reactions in conduits, but these only produce orthopyroxene or olivine with a similar magnesium number. That is, it cannot be responsible for increasing the magnesium number unless a high magnesium number parental magma was used. I too suggest that the Koffiefontein-Olivine magnesium number was increased through reactions with high magnesium melts. A possible high magnesium melt available in the Archean are bonanites, produced from melting within the mantle wedge in a subduction environment. An example of such a bonanite could be related to the Barberton area, where newly recognized bonanites have high magnesium number, high silica, and are depleted in incompatible elements. But once again, more research is needed in this area. So coming back to garnet formation and the requirement for orthopyroxene. Garnet in cratonic peridotites can occur from either exsolution from orthopyroxene during isobaric cooling, or from the reaction of spinel and orthopyroxene producing garnet and olivine. Using the chrome-aluminium contents of orthopyroxene and garnet, one can determine how these garnets were actually formed. By plotting coexisting garnet-orthopyroxene, it shows that a lot of the garnets from Koffiefontein plot in the orange region. That is, they formed by the reaction of spinel plus orthopyroxene gives you garnet plus olivine. Continuing with garnets, I'd like to move on to metasomatism. The Kaapvaal Craton has undergone extensive metasomatism. One end member for metasomatism is the introduction of rare earth elements, specifically the light LREE. Here is a LREE plot for the range of depleted garnets, Haasbergitic garnets, from the Kaapvaal Craton. Koffiefontein peridotic garnets show a sinusoidal pattern with extensive depletion in the heavy REE and enrichment in the light REE. Two types of metasomatic melts or fluids could be responsible. One is carbonatic melts or fluids. However, they react upon introduction to depleted peridotite, and extremely large volumes would be needed to create such a large enrichment. High-density fluids, on the other hand, carry dissolved incompatible elements and can readily percolate through depleted orthologies. HDFs can also create the variation in light REE enrichments as seen by the peaks at either cerium or neodymium, as shown in the circle. An extreme end member of metasomatism is the formation of new minerals. At Koffiefontein, a unique and highly fractionated metasomatic melt formed a new, never-before-seen mineral, which I got to name goldschmidtite. It is a potassium and niobium perovskite that accommodates other incompatible elements. And here it is, a picture of it in the diamond. The goldschmidtite inclusion is shown in the shiny green mineral, and surrounding the mineral is a brown radiation damage due to the radiation damage of the host diamond. Geothermobarometry on coexisting orgites gives its formation at 1,190 degrees Celsius and 5.3 gigapascals. Once liberated, the goldschmidtite was dark in color and opaque. Because it has a perovskite structure, this is what the mineral looks like, with the potassium in blue, the niobium in orange, and the oxygen in red. Pure KnBO3 is not cubic, but due to the substitution of smaller REE, goldschmidtite is cubic. Here's a table of the main constituents in goldschmidtite. I want to draw your attention to the rather high concentration of lanthanum at over 11%, and the 0.1 weight% thorium is responsible for that brown coloring of the diamond, the radiation damage. Also within this diamond is a tantalum-rich mineral. Analysis on this mineral are still ongoing, so maybe sometime soon I can update you. So for what I've presented on the inclusions, what does this mean for the Kaapvaal craton? The craton formed from an initial melt depletion event at low pressure, which resulted in a chrome-rich residue that was subsequently enriched in magnesium. During lithospheric thickening, garnet grew by the reaction of orthopyroxene plus spinel, and these garnets were later enriched by HDFs to produce the REE patterns seen today. Moving on to geothermobarometry. In a nutshell, it relies on inter-element exchange between certain minerals. And although you often need only the chemistry for a specific mineral, these thermobarometers rely on a specific set of minerals being present. So what happens for, like, when minerals are trapped in diamonds, you can't always infer that certain minerals are present. I've listed here a few of the common thermometers on the left and barometers on the right. And if you look at this long list, it seems reasonably easy to calculate pressures and temperatures from mantle minerals. But what if you have a Haasberg assemblage, like in the SCLM beneath Koffiefontein, where clinopyroxene is not present? A few options get taken off the list. And what if, like for diamonds, you don't have coexisting minerals? That list gets even shorter. And for some of these thermometers, they make use of trace element data that can only be obtained with ICP-MS. Enter Al-in-Olivine. For this project, I was able to make use of the updated Al-in-Olivine thermometer that relies on aluminium concentration in olivine. The aluminium concentration in mantle olivine is generally low, around 100 ppm, and down to 10 ppm in depleted rocks. And for Koffiefontein diamonds, it is one of the most common minerals and often occurs as a single phase within a diamond. For example, of those 91 minerals that are diamonds that are cracked open, 16 of them released olivine only. To be able to obtain such low concentrations of aluminium from small olivine inclusions, we relied on extended count times and an increased current from an electron microprobe. So we're able to measure down to 8 ppm aluminium. With this technique, I was able to add many more data points, 30 to be exact, than would be previously available. Unfortunately, it's not coupled to a barometer, and I projected it to my chosen geotherm, which I'll show in the next slide. In reality, this is what the olivine inclusions, once liberated and mounted in epoxy, look like. They are small, but they can be up to a few hundred microns in length, and the AL concentration is generally low, but it can be on the high side. For example, the highest value I recorded was 135 ppm, and the lowest, 13. On this diagram, temperature at the top and increasing pressure down the side, I've plotted the reference geotherms for Cratonic mantle. Before I get into the Koffiefontein data, I would like to emphasize that I've plotted the newer and more accurate Hashtag enchantment reference geotherms. You can see the difference in this inset here. For the purpose of this talk and the required range, a 40 milliwatt geotherm on the older Pollock enchantment is equivalent to the 38 milliwatt geotherm of a Hashtag enchantment. With the silicate minerals I recovered from the Koffiefontein diamonds, I used geothermobarometry to create an updated geotherm. All of the Koffiefontein data from both diamonds in colored symbols and Zenoliths in black symbols are plotted. The colors represent different geothermobarometric calculations based on the mineral or minerals present. By eye, you can see that the data points would suggest a 38 milliwatt reference geotherm for Koffiefontein. So for the olivine and eclogitic garnet clinopyroxene data, they are projected onto that geotherm. You may not want to believe my eye when I selected the 38 milliwatt geotherm. So using the program fitplot, I regressed the data separately for both the diamonds and the xenoliths. This produced geotherms that are within error of each other and within error of the 38 milliwatt reference geotherm. And that's just shown in the inset at the bottom left, how close they were. So what does this mean for the Craton and Koffiefontein? The diamond geotherm represents the Archean, whereas the xenolith geotherm represents the Cretaceous. Why has the geotherm not changed for almost 3 billion years? The Craton, being cold and stable, has most likely shielded its contents from changes to the ambient mantle. For large-scale heating events, such as intrusions that result in large igneous provinces, the heat was either rapidly dissipated or its effects had dissipated before kimberlite emplacement. Now that I've discussed the lithospheric mantle, I'd like to move on to diamonds from the lower mantle. The lower mantle is the largest reservoir by volume in the Earth. Most of what we know about the lower mantle comes from seismic studies, high-pressure mineral experiments, and some magmas that are thought to originate from great depths. Generally inaccessible, diamonds from the lower mantle can provide important information to the composition and processes within the lower mantle. Chemically, the lower mantle is similar to the upper mantle, but minerals adopt increasingly condensed structures to accommodate the increase in pressure. Here is a diagram showing the proportions of minerals of interest with depth. Highlighted here is the mineralogy of the lower mantle. It is dominated by bridgmanite, followed by ferropericlase, with minor calcium silicate perovskite. At the top of the lower mantle, a small window of majorite exists. Diamonds and the mineral inclusions have been actively studied since the 1970s. In their 2008 paper, Stockel and Harris included this important graph that breaks down the proportion of diamonds from the lithospheric, the transition zone, and the lower mantle. Very few diamonds have been studied from the lower mantle, and as such, our knowledge of the processes that form diamonds down there is limited. I aim to shed some light into diamond formation by using 3 lower mantle diamonds from Koffiefontein. So from Koffiefontein, 1 diamond hosted ferropericlase, as seen by the peacock coloring in this diamond. And 2 diamonds hosted ferropericlase and retrogress bridgmanite. Some diamonds also contained coexisting magnesite and magnesite alteration, and some unidentified silicate minerals that generally had low EPMA totals. Lower mantle diamonds are often dark brown in color and well resorbed in shape due to the high pressures and temperatures experienced in the lower mantle. Here is a close-up of ferropericlase, and in this image, it has a green color. Ferropericlase is not something that we often get to see, so I thought I'd include this picture. Worldwide, lower mantle diamonds generally have a mantle-like delta-13C and delta-15N values. However, nitrogen is generally very low compared to lithospheric diamonds. The Koffiefontein lower mantle diamonds have mantle-like delta-13C. Their range is plotted here off the diagram. Although generally low nitrogen, 2 diamonds had nitrogen-rich spots that are 15N depleted at -14 per mol, and they plot here. So what is the source of this depleted signature? As with the lithospheric diamonds, nitrogen from reduced sources could lead to highly 15N depleted diamonds, but this is not seen in the carbon isotopic signature, nor by the presence of carbonate minerals within these diamonds. Thus, like the lithospheric diamonds, their origin is still unclear. As with the lithospheric diamonds, lower mantle mineral inclusions within diamonds are not representative of the entire assemblage. The Koffiefontein lower mantle inclusions are similar in major element chemistry to lower mantle diamond inclusions from other locations, but plot towards the high magnesium side. In comparison to the experimentally produced lower mantle minerals from pyrolite, representative of fertile mantle, these Koffiefontein lower mantle minerals are extremely magnesium rich. This is a ternary diagram that shows the position of experimentally determined bridgmanite and ferropericlase from the fertile lower mantle, joined by tie lines. In the star symbols are mantle reservoirs of interest. For example, in the magnified inset, the red LZ stands for lozolite. Where these tie lines intersect a bulk rock composition, once again shown by the star symbols, this is their bulk rock composition. As expected, the experimental bridgmanite ferropericlase tie line intersects the field for lozolite. Here is the same diagram, but for the Koffiefontein bridgmanite and ferropericlase. Compared to the experimental data, their tie lines cross on the more depleted side of the diagram, closer to hasbagite and dunite. Thus, these minerals will need to come from depleted peridotite and not the fertile lower mantle as expected. So let's have a look at oxygen isotopes of diamond, of the minerals inside the diamond. For peridotic inclusions in diamonds, their delta 18O values is tightly constrained about the mantle range. For eclogitic inclusions, they have a large range that spans both 18O depleted and enriched values. And this is because they preserve high and low temperature seawater alteration imparted before diamond formation. Just to double check, this is the peridotic that has a really tight range, and here is the eclogitic that has quite a wide range. The same is true for lower mantle diamonds. Retrogress bridgmanite is tightly constrained around the mantle value, whereas transition zone and lower mantle inclusions derived from meta-eclogites have a wide range in delta 18O. So what is the substrate and fluid source of these rare lower mantle diamonds? The depleted lower mantle inclusions likely represent original depleted mantle that was attached to a deeply subducted slab. Although I don't discuss this in detail, the presence of magnesite indicates that diamond formation was a result of redox reaction of carbonate. The delta 13C of the diamonds could be produced from subducted slab or ambient mantle. Although the carbon has a mantle-like signature, the nitrogen isotopes are highly fractionated and could have an origin that was more reducing. To sum it all up, what are the lessons for the Kaapvaal Craton? The peridotic and eclogitic diamonds may have the same carbon source, and thus low concentration mantle-derived carbon need not be mobilized. This carbon is introduced through subducted slabs. The presence of carbonate minerals indicates the diamond can form by redox reaction in the depleted substrates. The high magnesium number of olivine cannot be generated by melt extraction alone, and it requires a peridotite that is likely metasomatic and occurred before Craton thickening. Lastly, the lower mantle diamonds demand a recycled component and provide evidence for volatile recycling into the lower mantle, a region that is thought to create a barrier to volatile recycling. Thank you for joining me on the journey through the mantle beneath Koffiefontein. Aside from the new information from the Koffiefontein that I've just shown you, I'm happy to report that I've added these analyses to the diamond literature. And I'd like to thank these individuals for their assistance with sample analysis and idea development.
Awesome, thank you.
Thank you. I hope I get a chuckle out of everybody. It's one of my favorite cartoonists.
That was good. Okay, well now we can proceed to the questions and answer part of this seminar. Feel free to unmute yourself, and you don't have to turn your camera on, but feel free to, and just ask your question. No need to raise your hand. Thank you.
No questions. Everybody understood everything. That's great.
I have just a brief question. I thought I saw someone with their hand up, but it's Tom McCandless. Did you mention the range of the stones that you looked at? I might have missed that when you said that at the beginning, or did you say the size or mass range?
No, I didn't. And you know what? I didn't actually size them. Jeff did. Well, I got them sized. They were kind of, there were some pictures that had sizes on them. Some of them were quite large, especially the eclogitic sulfide included diamonds were a few millimeters. I think I even had one up to like 2 centimeters. They're quite large.
Yeah, I saw some of your pictures look like they're quite big with the scale on there. Yeah.
Yeah. I've had to check that scale a few times because sometimes they do seem quite large.
Yeah, that's good. For the just one other question while I've got the floors. Your sources for C13 depleted carbon, I didn't see whether you had just bacteriological carbon as a potential source, right? Like the seafloor smokers have a lot of archaebacteria, which dates from 2.5 billion years. So just wondering if you thought about that.
So I did for the carbon. There were a few, if you remember that picture, it was down right at the bottom on the right. That's from the LREE paper where it has the biogenic, I suppose it's a carbonate, so it encompasses a lot of things that could come from it. And I did have some diamonds that plotted down there, even some peridotitic diamonds, but the majority, and that's what the kernel density plot showed, that they plot at -5.
Okay. All right, thanks, that's good work.
Thanks, Sam.
I'm not familiar with cracking open diamonds. How do you do that?
It's quite fun. You have a vise, it's about like this big, and it's steel, and you almost have something that looks like 2 pistons that hold the diamond together, a glass plate on each side, and then you just gently, depending on how tough that diamond is, and it just, because they're brittle, they just fracture, they break open. And if you do it in such a way, the inclusions don't break. And so you'll just get the diamond will fall out in between these windows, and you'll put it into a petri dish, look under a microscope, and sift through until you get the inclusions. So the majority of the inclusions came out whole or pretty whole, unless it was in a macle, and then you know you're screwed. They don't like to come out.
Okay, I'll go next then. Nice work, Nicole. A lot of people haven't looked at Koffiefontein for a long time. I think the last work on there was on the xenoliths was by Dave Bell. It's unpublished, so it's a nice locality to get back to. Interesting study. I wanted to ask your opinion about the aluminium in olivine thermometer, because I've seen, since it's been published and updated by Yannick Bussweiler, there's been a number of applications, and typically you get temperatures that are above the adiabat. You know, there's a lot of high temperatures in the aluminium and olivine thermometry that are out there. And your study is the first one where I see no temperatures above the adiabat using the same thermometer. Do you have an explanation for that?
Well, I don't have an explanation, but I'm so glad you asked. This was one of the questions that related to my defense. So for a lot of the, like the Harley thermometer, where I had the orthopyroxene garnets, the error on it is actually quite large. It can be up to 150. Yeah. And I think in Yannick's paper, he says that on the aluminium and olivine, the error is quite low. It's 80 degrees Celsius. So it's actually quite nice. I know I had nothing that plotted in terms of the aluminium, nothing that plotted on the adiabat. In terms of the Harley thermometer, a few plotted on the other side of the adiabat. And I just wonder if we talk so much about aluminium being a trace element in olivine and how it's not as easy, and there's not a lot of it to really, olivine doesn't like, it can't be as easily metasomatized in terms as garnet can be. So it should be more robust. But maybe it's the studies with the xenoliths where there's been a lot of later metasomatism that you're getting the much higher temperatures that are artificial, but everything seemed happy. And I got such great values, but my data points, nothing went over 135 ppm aluminium. It was between 11 and 135. So that could be it. They may have to have a cutoff range.
Okay, no, that's good, thank you.
May I ask you something, Nicole? So thanks a lot for your interesting talk, first of all. And I'm impressed with your photographs. The photographs of diamonds with inclusions, absolutely amazing. So are these images stacked images? Like, do you have any tips for us how we can do as good as you?
Well,
I think.
Thanks, Maya. I was actually telling Thomas this week that for DIRTs, Aneta should run a show on how to take great sample images. I took a lot of Aneta takes great images, and I had to take a lot of that from her. Everything was done under a binocular microscope with just a normal DSLR image, except for the two of the sulfide. So they weren't stacked, just straight images and getting the focus right. It's really about time spent getting the best image, a lot of lights. The two with the sulfide, that was actually done under the Raman microscope. And there was something about it that just gives, I think it's just a high magnification. You can just get some great pictures. And it's really just, I suppose, luck and working hard at it.
Isn't one of Aneta's secrets, which she might kill me for divulging, is to have the diamond on a glass slide above the surface that you're photographing, so that there's no shadow cast beneath?
Yeah, you kind of do forget that. So we do a glass slide with little stands, and you don't get any shadow in that. There are a few things, especially using like the DSLR camera, you just have to make sure that you have set it to get enough light in. You use a lot of octopus arms and a very long time. Most of these diamonds, I actually took pictures just before the Christmas break when I started. So the lab was nice and empty, nobody was around, and you can really put on some music, put on a podcast, and just take lots of pictures. That's kind of how it went. I probably have about 300 gigs of raw photos saved on the Google Drive of all the pictures that I've taken. They're hundreds. Oh, and I should add that as part of my thesis, all of these pictures that I've taken are going to be available on an online repository at the University of Alberta. So when the thesis is available in 6 months' time, it will be there with it.
Nobody else? Okay, I'll go again.
Okay, Herman.
Nicole, you had some very high chrome subcalcic garnets.
Yes.
There's inclusions in your diamonds.
Yeah.
If you calculate pressures for those, assuming that they were, either with chromite or without chromite, but they were in equilibrium with OPX, those pressures would be very high.
They are, because I did calculate it.
What do you make of that number?
Well, there were not a lot. There was just some that had the really high chromium. So I'm not sure if that would be a standard environment, or if it would just be something that occurred once, some sort of metasomatism that happened and we haven't seen. But yeah, they have also pretty high pressures calculated on the chrome. And also if you're having a very chrome-rich residue, you can also make chrome-rich garnets. So I don't have an exact answer for you, Herman, but.
Are there any other questions? Nope. Okay.
I'd like to ask a question.
Oh, great.
About the quality of the diamonds. Where are the best diamonds found? Like in what groups are they found? And how about also when they're being retrograded? I guess you showed a graph near the beginning. And do you get, fairly good quality? And also, can you do anything with the diamonds, like commercially, the ones that have twinning and striations and that, or?
So in terms of the diamonds, the 200 diamonds that I got are only going to be inclusion bearing. So in terms of what the Koffiefontein production looks like, I can't remember offhand, but there is a 1979 or 1975 study that Jeff Harris and John Gurney did about the actual diamonds. And unfortunately, Koffiefontein hasn't been in production continuously. It's currently being remined now by Petrodiamonds. In terms of the quality of the diamonds that have the sulfides in it's really hard to explain, but they were so large, so colorless, but they had these massive sulfides inside. And they also were perfect dodecahedroids, most of them. Dodecahedroids for most of them. In terms of the prototypic diamonds, they were often octahedra, but with a lot of surface features. And the eclogitic proportion in terms of silicate eclogitic diamonds, quite small, but they're generally irregular. Definitely some scatters of brown diamonds throughout. In terms of the diamonds with the striations, if they can do something with them commercially and with the macles, I don't know. I have polished a lot of diamonds. The macles are really hard to polish, but I think that they have to do something with them.
Okay, thank you.
Sure. Okay.
If anyone is also feeling shy, you're welcome to write your questions in the chat as well. Okay, and I'll say with that, maybe we'll start to transition to the social pub hour sort of virtual part of VKC that we're missing because we're not in person. So I would suggest if you want to stick around and socialize with some of your Kimberlite friends, feel free to stay or grab a beverage, and I will stop the recording. So yeah.